Let's look at this practice midterm exam. Before we start talking about the actual problems, let's look at the overall requirements. You are required to report your final answers in 3 significant figures. And you should use scientific notation when necessary, meaning that if your answers are too big, more than 1,000, or too small, smaller than 0.001, for example, then those answers need to be expressed using scientific notation. Or you can switch to a more appropriate units. You should include free body diagram for any problems that involve force analysis. And very importantly, you have to include all the necessary steps as well as the appropriate units. Your answers are not considered correct unless they are of the correct numerical values as well as they have the correct units. And lastly, you need to box your final answers. So make sure you do that for all of your problems in your exam. So let's look at the first problem. We need to determine the force in the cables and the stretch in the spring, that will be spring AB, for the equilibrium to support the 50-pound load as shown. Cable AD lies in the XY plane and cable AC lies in the XZ plane. So this is a 3D particle equilibrium problem. And the very first thing you want to do is to draw the correct free body diagram. So we want to draw the free body diagram at the particle, which is the knot at point A. So at point A, we have the given force, 50-pound force, that's the load that's given. And then we have the spring force, FB right here. That will be from A to B in the direction, simply along the Y direction. And then we will have the force that will be tension force from A to C. And lastly, we have another tension force that is from A to D. So that completes the free body diagram. So the next thing you want to do is to represent your forces into vectors, and then we will add all the vectors together, and we will apply Newton's first law to set the vector equation to 0. And for a 3D particle equilibrium problem, that translates to 3 scalar equations all set to 0, and then we will have our system of 3 equations, and from there we can solve for 3 unknowns. So even though eventually we want to solve for the stretch of the spring, but for now we can solve for the 3 magnitudes of the 3 forces, and then from there, FB equals to, if you remember from Hooke's law, the coefficient of the spring times the stretch, and from there we can solve for x. All right, so as vectors, our load is going to be negative 50 in the direction of k, all in the unit of pound. Okay, our FB spring force, that'll be a magnitude of FB only in the y direction, so only has a j component. Okay, our TAC vector, the direction is given by the 3, 4, 5 triangle. So negative 4 over 5 along x direction, positive 3 over 5 along the z direction. So that will be your magnitude, TAC, times. All right, negative 4 over 5, I. And then we will have positive 3 over 5, k. And by the way, this is the unit vector UAC. And we will have TAD. This angle right here is given as a 30-degree angle. So we will have sine 30 degree along the x direction, and then a negative cosine 30 degree along the y direction. So we will have the magnitude TAD. All right, and then positive sine 30 for I, okay? And then, so this is not divided by. This means that this portion is unit vector, right? And then minus cosine 30 degree, okay? That's along the, that has a j component. So this right here inside is your unit vector UAD, by the way, as well. Okay, so the directions are pretty easy to determine. So I did not really use the position vectors to determine the unit vector. So it was relatively easy to determine this way. If the problem is more complicated, like some of your homework problems as well as your quiz problems, you are given the coordinates of points. You will need to use position vectors and then to find unit vector from the position vector and then attach the unit vector to the magnitude to get your force vector. All right, so now the equation is to summarize all these four vectors and then set that sum to 0. And that translates to three scalar equations. We have along the x direction, resultant force along the x direction. We don't have anything from the first two forces, but then from here we have a negative 4/5 TAC. And then from the last one, we have a sine 30 degree TAD, and that equals to 0. Along the y direction, nothing from the first force. From the second force, we have a FB. And then from nothing from the third force, but from the last force, we have a cosine 30 degree TAD equals to 0. And lastly, along the z direction, from the first one, we have a negative 50. Nothing from the second one. From the third one, we have 3/5 TAC equals to 0. Okay, so we summarized all the forces together in each of the three directions. Because of equilibrium, we apply Newton's first law. We set the equations to 0. Three equations, three unknowns. We can solve for all three of them. So probably easiest to solve for TAC from the last equation first, and then substitute that into the first equation to solve for TAD, and then from there solve for FB. Either way, you should be able to solve for all three of them. Therefore, we will have our FB, which is the spring force, that is 115.5 pound. Yes, that's four significant figures, but we're not done yet, right? I'm still gonna use that to solve for the stretch. And then my TAC is 83.3 pound. And then my TAD is 133 pound. And because my spring force equals to 115.5 pound, which equals to Kx, the spring constant is 300 pound per foot multiplied by x. From there, you can solve for x, which is the stretch of the spring, and that equals to 0.385 foot. So that's the answer for this problem. The two tension forces in cable AC and AD, as well as the stretch of the spring. Okay.